oxidation and damping. So free oxidation occurs when no external forces act on the system and there's no loss of energy from the system. So the amplitude of free oxidation does not change over time, which means the amplitude is maintained. And it's also important to note that the frequency of free oxidation is the natural frequency of the system. Let's now take a look at damped oxidation. Damped oxidation occurs when total energy of the body in the oxidation is lost from the system. So the amplitude over time decreases. There are three levels of damping. Let's start off with light damping. During light damping, the amplitude of the oscillation gradually reduces over time. What is critical to note is that the period of oscillation remains unchanged. So this is the graph for light damping, and you can see that the period of one oscillation, and the period of the second oscillation, and the period of the third oscillations, those timings are more or less the same. So basically, the period of the oscillation remains unchanged for light damping. Critical damping. In the case of critical damping, oscillations are being damped in the shortest possible time. In critical damping, the period of the oscillation goes to zero as the displacement is very quickly brought down to zero. So meaning to say that the object has stopped oscillating. So when it stops oscillating, the period of oscillation must be zero. Next one we look at is heavy damping. Heavy damping occurs when the damping applied is greater than that of the critical damping. So in this case, the system will be heavily damped, and it will take a long time for it to return to equilibrium position. So very much like a door, whereby the damper is already damaged, and when you open the door, it takes infinite time for the door to close. So in this case, the period of oscillation goes to infinite. Next, we'll now take a look at forced oscillation. Unlike free oscillation, in the case of forced oscillation, the system is being exposed to an external periodic force that causes the system to oscillate at any frequency that the system is being driven. So the amplitude of a forced oscillation depends on first the frequency of the driving force and also the natural frequency of the oscillating system. And the natural frequency, as we explained earlier, is actually the frequency of the free oscillating system. By looking at the displacement versus the driving frequency, we note that when the driving frequency is zero, there's actually a certain displacement. And more importantly, as the driving frequency goes towards the natural frequency, the displacement will increase significantly. So at this frequency where F equal to F naught, this is what we term as the resonance frequency. Because at the resonant frequency, there's the maximum transfer of energy from the driving system to the system being driven. Finally, let us take a look at the effects of damping. The effects of damping on the amplitude of forced oscillation. When there's actually very light damping, this is actually the graph, very similar to the graph earlier that we have discussed. But when the damping increases, the maximum amplitude of the forced oscillation start decreasing, and you can see that the frequency at which the system oscillates at its maximum amplitude decreases as well. So at light damping, this is actually the resonance frequency. But when the damping becomes heavier, the resonance frequency actually decreases. So with or without damping, I think it's important to take note that all the system has the same amplitude of oscillation when the driver frequency is 0 Hertz. Finally, when there's no damping and the frequency is equal to the resonance frequency, that is where the amplitude of the forced oscillations can go to infinite. So for example, like in the case of a glass, if the pitch or the frequency is high enough, then the glass will oscillate with an amplitude that is infinite, and that causes the glass to actually shatter.